All right, so notice that we're kind of beating around the bush here. And instead of telling you what continuity is, I've told you what continuity is not. I've given you examples of discontinuity. Okay? Well, functions are continuous everywhere else. All right? If these things don't happen to force discontinuity, then the function is continuous. And when we talk about continuity, we've got to talk about on an interval. Because many functions can have discontinuity, but be continuous everywhere else. All right? So some functions are continuous for all real numbers, like sine and cosine, like quadratic and cubic, polynomial functions. Okay? Those are continuous for all real numbers. But lots of functions can have discontinuities, like the ones when we were finding limit, when if you substituted, you'd get a denominator of 0, but we could mess with them algebraically and still find the limit by substitution after doing that. Those would have holes in them, okay? So they would be discontinuous there when that happens. So, but they're continuous everywhere else, except for where the hole was, or the two holes, or however many it happened to have. So, if none of the above three conditions is true, the function f is called continuous at c. Okay? So if there's not a reason for a function to be discontinuous, then it's continuous. Now, they give us the definition of continuity, and we're going to use it. But before we get to the definition, do you feel like you have something of an intuitive idea of what continuity is? All right? The most basic thing, and this is a little bit oversimplistic, but a function is continuous if, once you put your pencil down to start graphing it, you don't take your pencil back up off the paper. That's continuous. If you do take the pencil back up off the paper, function is discontinuous there. Once you put your pencil back and start drawing again, it's continuous again until you have to take it up again. Okay? Let's see the definition. Continuity at a point. We're going to go from continuity at a point to continuity on an interval, and maybe even to continuity for all real numbers. Continuity at a point. A function f is continuous at c if the following three conditions are met. So f of c is defined. Well, that's kind of the opposite of saying f of c is not defined, led to a discontinuity. So f of c is defined. That doesn't prove it's continuous. That's one condition for it to be continuous. All right? The second thing that led to a discontinuity was the limit not existing. So the second condition to be continuous is the limit of f of x as x approaches c exists. Okay? The third thing that we looked at that led to a discontinuity was that the limit didn't equal the value of the function, even though they both existed. So, to make it continuous, the limit does equal the value of the function. They both exist, and they're equal to each other. F of c exists, the limit exists. They're equal to each other. All three conditions must be met, and when they are, we say that the function is continuous at x equals c. Okay? Yeah. All right, that's what this guarantees. No hole. Okay? So, the function has to exist at c, the limit has to exist as x approaches c, and the value of the function at c has to equal the limit as x approaches c. Those things guarantee continuity. Right? And look back to this. Here's what happens if the first condition's not met. Here's what happens if the second condition's not met. Here's what happens if the third condition is not met. So all three conditions have to be met for it to be continuous at x equals c. You'll need to know those three conditions. Okay? You'll need to know those. So, A function is continuous at x equals c if f of c exists, if the limit of f of x as x approaches c exists, and if the limit of f of x as x approaches c equals f of c. So that's continuity at a point. Continuity on an interval, an open interval. Okay, open means that the endpoints may or may not be included, in fact aren't included. A function is continuous on an open interval from A to B. Now, pay attention to the context, because isn't that the same notation we use for the coordinates of a point? Yeah, so pay attention. They'll say interval, all right? So a function is continuous on an open interval from A to B if it is continuous at each point in the interval. Okay? So if you've got an interval from 4 to 7, and our function is continuous for every number between 4 and 7, then our function is continuous on the open interval from 4 to 7. And a function that is continuous on the entire real line, a function that is continuous for every c, is continuous from negative infinity to infinity, or is everywhere continuous. And a lot of people say continuous for all real numbers. So those all expressing the same idea. If a function is continuous from negative infinity to infinity, or if it's everywhere continuous, or if it's continuous for all real numbers, that all means the same thing. And what it means is it's always continuous. There are no places where the function is not continuous. There are no places where the function is discontinuous. Okay? Now, I kind of like the way the book presents continuity. To me, now I've been doing this a while, okay? To me, it kind of makes sense to see the things that make the discontinuities, the conditions guarantee that those things that form the discontinuities don't happen. So those are the conditions that have to be met for a continuous function. Okay? All right, so far so good. Now, not all discontinuities are created equal. There are removable discontinuities and non-removable discontinuities. Short version. A removable discontinuity is one where all you have to do to make it continuous is to fill in the hole. Other than that, it's a non-removable discontinuity. So if we look at these again, the first one, that's a removable discontinuity. Because all we have to do to make it continuous is figure out how to fill in the hole. And we will have to figure out how to fill in the hole. The second one is a non-removable discontinuity because there's a big gap in there. I could fill that in. That doesn't help. All that does is make it not a function anymore, doesn't it? So that's a non-removable discontinuity. So what would the third one be? All right, the dot is non-removable, but what if I can erase that and fill that in? So I'm not sure, am I? Okay? As it is, I would say non-removable because I can't fill in the hole. But if I can erase the point down here, and maybe I can, piecewise defined function, I can change one of the pieces and move it up there, then I can make it. So we're ambivalent, or not ambivalent, what's the word I'm looking for? Uncertain about that. Okay? Now, let's see then. So I'm uncertain about that. Let's see if we can find a way. Here's my note. All right, a removable discontinuity at x equals c is a discontinuity where the function can be made continuous by redefining f of c. Oh, if I get to redefine f of c, I probably can move that point from down here remove it from there and move it up to there, can't I? If I get to redefine f of c. All right? I.e., in other words, a discontinuity is removable if you can redefine f of c to fill in a hole in the graph. Another way to tell if a discontinuity is removable, use analytical methods to find a function that is equivalent at all but x equals c. We did a bunch of those, didn't we? That's when we were doing the dividing out. All right? If you can do that, then you have removed the discontinuity at x equals c. That's what we were doing. When we had that function that looked like that, and then we factored it, and then we got to divide out the x minus 1, and we were left with a polynomial. The polynomial function was continuous everywhere, and we could find its limit. So we didn't know it at the time, but what we were doing is we were removing the discontinuity. We were making it so that the hole was filled in. Okay? So you already know how to remove discontinuity. You just didn't know that's what you were doing. Okay? Yes, except the hole's filled in. Because that's what happened there. Because remember that was something like that. And then once we factored that, is that the right factorization? We did that. Then when we graphed x squared plus x plus 1, it looks exactly like this graph, except the hole's filled in. So we took a function that had a discontinuity at 1, replaced it with a function that did not have a discontinuity at 1. We redefined the function, which we can do. And that removed the discontinuity. You with me? All right. So, let's look at what the book has to say about this. It says, consider an open interval I that contains a real number c. If a function f is defined on this interval, except possibly at c, and f is not continuous at c, then f is said to have a discontinuity at c. All right, so that just kind of sums up in math talk what we've been talking about. If it's discontinuous because one of those three conditions is not met, or one of those three bad things happens, it's discontinuous. Now, discontinuities fall into two categories, removable and non-removable. A discontinuity at C is called removable if f can be made continuous by appropriately defining or redefining f of c. So, like we were talking about, that first condition where f of c does not exist, that's removable. We just have to make a piecewise function or divide out or whatever and tell what f of c is going to equal to fill in the hole. When there's a gap, that's non-removable. And here, the one that we wondered about, once we said we could redefine f of c, that makes that removable. We redefine it so that f of c does not equal that and does equal that. Okay? And we've been doing this all along because we've been coming up with equivalent functions. We say equivalent functions, what we mean is that they are equivalent at all but one point. So now we're that fixing that one point where they're not fixes the discontinuity, removes the discontinuity. Okay? Questions? All right. All right, look at this one. A here. Non-removable discontinuity at x equals 0. Because look, here's x equals 0. You can't just fill in a hole, can you? You can't just fill in one point and make it continuous. So, non-removable. Look at B. This discontinuity is removable because all you have to do is fill in the point 1, 2. Okay? How would we do that? rewrite it, call it f of x now instead of g of x, and that's a continuous function, and there's not a hole at the point 1, 2 anymore, is there? We removed the discontinuity. Whenever you divide out the factor that's causing the denominator to equal 0, you are removing the discontinuity. Oh, that was important. I'm going to say it again. Whenever you divide out the factor that is causing the denominator to equal 0, you are removing the discontinuity. Yes? Yeah, for a slightly different purpose. Instead of solely worrying about limits, now we're worrying about limits and continuity. Okay? All right. Graph C is continuous everywhere, so it's continuous for all real numbers. It's continuous from negative infinity to infinity. It's continuous on the entire real line. It's everywhere continuous, even though it's a piecewise function. Piecewise, defined in two pieces. Because look, the top piece, x plus 1, that's a line. That's continuous. The bottom piece, x squared plus 1, that's a quadratic, or better yet, that's a polynomial. That's continuous. So as long as they connect at x equals 0, when you connect two continuous pieces, as long as you literally connect them, there are no discontinuities, are there? So it's continuous everywhere. The sine of y equals the sine of x. Continuous everywhere. Okay? You still think you're hanging in there with me? Yep. Yep. All right. One-sided limits and continuity on a closed interval. We've talked about one-sided limits. We've talked about, hey, as x approaches 2 from the left, we get this, and as x approaches 2 from the right, we get this, haven't we? And if x approaches 2 from the left, gives you the same thing as you get when x approaches 2 from the right, we said that that was what the limit was. That's what all those tables were doing, isn't it? That we made, all those tables of values. When they gave us a graph and said find the limit, that's what we did. Go back to this one. All right, look at the middle one. As x approaches c from the left, we get that y value. As x approaches c from the right, we get a different y value, so the limit does not exist. But look at case 1. As x approaches c from the left, we get that y value. As x approaches c from the right, we get the same y value. They're approaching the same y value from the left and from the right. So that limit does exist, doesn't it? Okay? So we've talked about one-sided limits before. Here I am. So, to do the one-sided limit notation, a little positive sign as a superscript goes where the exponent goes. On C means from the right, and from the right means values greater than C. A superscript of a negative sign means approaches C from the left. From the left means values less than C. If the limit from the left equals the limit from the right, then either the function is continuous or it's a removable discontinuity. Okay? When the limit from the left equals the limit from the right, either the function is continuous, or if it's discontinuous, it's a removable discontinuity. Okay? So if there is a discontinuity at x equals c, and the limit as x approaches c from the right equals the limit as x approaches c from the left, the discontinuity is removable. So does that give us another way of knowing when a discontinuity is removable? Yeah. When most often does this apply? Usually when we're looking at the graph. Okay. Now, when the limit from the left is not equal to the limit from the right, then the limit does not exist. Okay? So if the limit from the left equals 4, and the limit from the right equals negative 12, the limit does not exist. Okay? So the one-sided limits have to equal each other for the limit to exist. And that's what this next theorem says. It says the existence of a limit. Let f be a function and c and l be real numbers. The limit of f of x as x approaches c equals L if and only if the limit of f of x as x approaches c from the left equals L, and the limit of f of x as x approaches c from the right equals L. So, most of the time, so far, we've not had to worry about this. Okay? We talked about one-sided limits looking at graphs, but working things out analytically, we just found the limit, or, well, we found the limit either successfully or unsuccessfully. Okay? But now you got to know, for the limit to exist, the limit from the left and the limit from the right must equal each other. And the thing that they both equal, that's the limit. All right. Yeah. Yes. 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 All right. Like this. The greatest integer function. That's what this crazy looking bracket thing is meaning. That double bracket on each side of the x. That's called the greatest integer function. Now, the word greatest confuses people in math sometimes because it always makes you think bigger. But like if you have two numbers, 3 and 6, the greatest common factor of 3 and 6 isn't 6, it's 3. Because we got to remember common, the biggest common factor. Well, greatest integer function is the biggest integer less than or equal to a number. So the greatest integer of 2.5 is 2. The greatest integer of 2.9 is 2. The greatest integer of 2.99999 is 2. Negative numbers can mess with you. The greatest integer of negative 2.5. All right, so let's find negative 2.5 on a number line here. So negative 2.5 would be right about there. If I make that number line keep going. What's the greatest integer less than or equal to negative 2.5? Negative 3. All right? Isn't it? Name an integer bigger than negative 3 that's less than or equal to negative 2.5. You can't. So negative 3 is the greatest integer of negative 2.5. So I just taught you how the greatest integer function works. And look at its graph. Guess what a graph like that's called? Called a step function. Okay? It's called a step function. That function is discontinuous at every integer, isn't it? Okay? And those discontinuities are non-removable, aren't they? Because it's a big old step you got to take from one horizontal line to the next. You can't just fill in a hole. Less than or equal to. So the greatest integer of 3 is 3. It's in there somewhere. We'll look for it later. Does that make sense, Charlie? So you would write it like this. F of x equals the greatest integer of x. And then the greatest integer of a number is the greatest integer less than or equal to that number. So the greatest integer of 7.2 is 7. The greatest integer of negative 0.1 is negative 1. Okay? All right. So step functions, discontinuities. All of the properties, theorems, and techniques that apply to regular limits apply to one-sided limits. Many times, when the limit of f of x as x approaches c does not exist, one or both of the one-sided limits will exist. Okay? They just don't equal each other, that's all. One-sided limits are commonly used with radical functions, absolute value functions, and greatest integer functions. Can you see why you might want a one-sided limit on a greatest integer function? What's the limit of that function as x approaches 1 from the left? 0. What's the limit as x approaches 1 from the right? 1. So we can still talk about limits from one side to the other, even though we can't talk about the limit as x approaches 1, because it doesn't exist. Okay. Let's see, I'm looking for something that apparently I don't have on here. Back to here. One-sided limits and continuity on a closed interval. Okay, because we're going to get to it tomorrow. Let's do some examples. Page 78. Number 4. Use the graph to determine the limit and discuss the continuity of the function. So for A, we're supposed to find the limit of f of x as x approaches c from the right. B, the limit of f of x as x approaches c from the left. C, the limit of f of x as x approaches c. So for number 4, they tell us that c equals -2. So look, I've already turned it into what I need. So A is to find the limit of f of x as x approaches -2 from the right. B, the limit of f of x as x approaches -2 from the left. And C, the limit of f of x as x approaches -2. All right. As x approaches -2 from the right. So you're moving along the function. X is approaching -2 from the right of -2. And what's the y-coordinate keep getting closer to? 2. Then to find the limit of f of x as x approaches 2 from the left. You move the x's closer to -2 from the left. And what's the y-coordinate approaching? 2. Since the limit from the right equals 2 and the limit from the left equals 2, the limit equals 2. So we found the limits. The directions also said discuss the continuity of the function. It's easier to discuss continuity by actually discussing discontinuity. Does that function have any discontinuities? Yes. At x equals -2. F is discontinuous at x equals -2. How come? Because our 3 conditions. F of c exists, the limit of f as x approaches c exists, and the limit equals the function value. F of c exists, the limit exists, but they're not equal. That's why it's discontinuous. Because f of -2 is 3, but the limit as x approaches -2 is 2. So the first 2 conditions for continuity were met. F of c existed, and the limit as x approaches c existed. But they're not equal to each other, so the function's discontinuous there. Okay? Number 6. We need to find the limit of f of x as x approaches negative 1 from the right. Well, as x approaches negative 1 from the right, what's the y-coordinate going closer to? So the limit as x approaches negative 1 from the right is 0. Now, x needs to approach negative 1 from the left. As x approaches negative 1 from the left, what's the y-coordinate getting closer to? 2. Since the limit from the left does not equal the limit from the right, what's the limit as x approaches negative 1? D and E does not exist. So, let's discuss the discontinuity. Well, where's this function discontinuous? Yeah, f is discontinuous at negative 1 since the limit of f of x as x approaches negative 1 does not exist. Do we have good reasons now? We don't have to say gap, hole, asymptote. We say f of c is not defined, or we say the limit does not exist, or we say the function value and the limit do not equal each other. It's one of those three reasons to make a function discontinuous at a point. Hang on. All right, we good with 6? Let's try something more difficult, like 9. Find the limit if it exists. If it does not exist, explain why not. All right, number 9. I'm going to lead you down a false trail first. I told you ahead of time. We have the limit as x approaches negative 3 from the left of x over the square root of x squared minus 9. All right, I can't use substitution because that would give me a denominator of 0. So I try multiplying by the square root of x squared minus 9 over the square root of x squared minus 9. That gives me this, and I still can't use substitution. Okay? So, let's try it again. This time, we're going to use a theorem that we've talked about way early on and really haven't talked about since, and it's this. Whenever we have the limit of a quotient, we can make it the quotient of the limit. We do it that way all the time. We just never say it that way. And we don't ever write it like this. So, write it like this. Make it the limit of the numerator divided by the limit of the denominator. We work them that way. We just don't write them that way. Well, now we're writing them that way. Negative 3 from the left. All right, the numerator, I can figure out that limit by substitution, can't I? Okay, the limit of x as x approaches negative 3 from the left is negative 3. But the denominator, I can't substitute. So instead, I'm going to reason. Ooh. If x approaches negative 3 from the left, well, as x gets closer to negative 3, when you square that, it gets closer to 9, doesn't it? Now, since we square it, as x is approaching negative 3 from either side, well, from the left, as x is approaching negative 3 from the left, like negative 3.1, negative 3.01, negative 3.001. When I square that, is the result of squaring that bigger than 9 or smaller than 9? 3.1, or negative 3.1, bigger than 9 when I square it. Negative 3.01, bigger than 9 when I square it. Negative 3.000001, bigger than 9 when I square it. Now, something bigger than 9 minus 9 is positive. So I can have a positive under a square root, can't I? If it was negative, I'd be in trouble. But I can have a positive. So look, so my denominator is approaching 0, isn't it? Because that's something bigger than 9 minus 9. It's going to get closer and closer to 0 as our number gets closer to -3. Okay? So our denominator, our expression under the radical is approaching 0 from the positive side. The square root of something approaching 0 from the positive side would be itself positive and approaching 0, would it not? So the denominator is approaching 0. And I really should have put it from the positive side, from the right. Now, how many times can 0 divide into a number? It can't. We've always said it's undefined. But think about it. An infinite number of times, really, right? Think about what it goes into. I've got a bucket here that will be full when I fill it to -3. And I throw a 0 in there. And another 0, and another 0, and another 0, and another 0. I can divide 0 into -3 an infinite number of times. So, we still don't have a definition of dividing by 0. But when we're talking about limits, the limit of a constant divided by something approaching 0 is infinity or negative infinity. Just get the sign right. So in this case, since it's a -3, it would be negative infinity. Now, let me back up. Hang on, let me back up. Does dividing by 0 exist? No. So the limit does not exist. It doesn't. I'm not trying to convince you that it does. However, a better representation of what's going on than simply saying does not exist is negative infinity. Hang on. Charlie had a question first. Uh-huh. Uh-huh. Because it's positive. If we had a negative under a square root, that would throw everything off, wouldn't it? If you don't want to put the positive, I'm fine with it. Well, because I know that when I square as those numbers approach -3, and I square it, it's a result bigger than 9. So something bigger than 9 minus 9 is positive, even though it's really, really small. It's almost 0, but it's still positive. And the square root of something that's almost 0 but still positive does exist. Whereas the square root of something negative doesn't exist. Okay? You're overthinking it. You just need to think about that right there in and by itself. Okay? And what I have highlighted in yellow, that's always going to be a little bit bigger than 9. The closer x gets to -3, the smaller the difference between x squared and 9. So as x approaches -3, the difference of x squared and 9 gets closer and closer to 0. Right? The difference will always be positive because x squared is always bigger than 9. So that's the reason I put the little from the right. Just from the positive side. Okay? All right. Lucas, you had a question? Alex? Because it was a -3 divided by, if it had been a +3, we'd say positive infinity. Your signs still work out. The way you divide with positives and negatives still work. So that's why. Let's do 11 real quick. This is another thing you got to think through. We have the limit of the absolute value of x over x as x approaches 0 from the left. Now, Here's the nice thing about absolute value signs. Sometimes they're completely meaningless, aren't they? If the expression inside the absolute value sign is positive, the absolute value signs do nothing. If I write down the absolute value of 5, and then on the next line I leave off the absolute value signs and just put 5, it's still correct, isn't it? If I have the absolute value of -5, on the next line, I can't put -5, can I? Because if the expression inside the absolute value sign is negative, the absolute value signs change its sign. So the absolute value signs do one of two things: nothing or change the sign. Okay? So if x is positive, the absolute value signs do nothing, and I can leave them off. If x is negative, the absolute value signs change its sign. If x is approaching 0 from the left, x is negative. And if x is negative, the absolute value signs change its sign. Now here's the part people get confused on. To change the sign of a number, put a negative sign in front of it. If I have -5, how do I change its sign? Put a negative sign in front of it. So, if I need to change the sign of x, put a negative sign in front of it. And now, -x divided by x is -1, and I can find the limit of -1. The limit of a constant is the constant. All right, bear with me just another minute. Is that? All right. There's your assignment.